did you have? We'll find
I
out here
had
in a second.
the Heck reaction.
Oh, okay.
Okay, so my palladium catalyzed cross-coupling reaction was the Heck reaction. I believe that like Emily might have had this in one of the synthesis presentations.
I think that's
So
right.
the Heck reaction, the functional groups that are involved in it, well, the Heck reaction, it couples alkene, alkeno or aryl halides, such as iodides and bromides, carboxylic acids or triflates, and carbonyl groups such as aldehydes, amines, esters, and nitro groups. It couples a lot of different functional groups, and it tolerates them to the vinyl carbon atom of alkenes. So for the catalyst portion, the Heck reaction, it proceeds in the presence of a base, and usually a phosphine ligand is also present during the reaction. In the reaction down here, you can see that they use triphenylphosphine, and the generally used bases in this reaction are secondary or tertiary amine, sodium or potassium acetate, carbonate or bicarbonate. And the catalyst in this reaction that's commonly used is palladium acetate. However, palladium chloride or performed triaryl phosphine palladium complexes, as well as palladium charcoal, have also been used to do this reaction. So this is this is an example of the type of reaction that is the Heck reaction. You have an argon with a functional group added to a methyl arsenate with the in the presence of a base, and then you have the.
Can I interrupt for a second?
Sure.
So AR is,
that's
an abbreviation for an aryl group. So that
group?
just means, yeah. So that, yeah, I know it's a very unfortunate abbreviation, right? Because it of course is an elemental symbol, but AR is any aromatic ring. So it could be just like benzene or naphthalene or some hydrocarbon one, or like one with nitrogens or oxygens or whatever. So any aromatic ring.
Okay. So yeah, so you see that it's the catalyst is the palladium acetate, and then you have the triphenylphosphine, and in the presence of a base to yield this. And I wasn't quite sure what the name of this would be then. Like the product.
Yeah. So that. Okay. So an aryl ring. So if imagine that aryl ring is just a benzene ring.
Mm-hmm.
Then a benzene ring with an alkene with a conjugated carbonyl on it, that sort of like chunk actually has a specific name. So those are called a cinnamoyl group. So for example, if the carbonyl was an aldehyde, that would be cinnamaldehyde. If it was a carboxylic acid, it would be a cinnamic acid. So that molecule, if the aryl group was benzene, that would be the methyl cinnamoyl ester.
Okay.
Yeah.
Good to know.
Yeah.
Thank you.
Yeah. And FYI, fun fact. Oh wait, I might be wrong about this. Yeah, I'm not going to say it because I'm not totally sure. Okay.
Okay. So this is an image of the catalytic reaction. So in step one, it starts off with the oxidative addition of a polar substrate onto a palladium catalyst to form a tetrasubstituted complex. Then in part two, you have the migratory insertion of an ophaline into the system. Then in step three, you have the beta hydride elimination of the alkene, I guess in this area. And then in step four, you have the addition of base to the palladium to regenerate the starting catalyst and close the cycle. And that's the Heck reaction.
All right. And that cycle probably looks familiar to a lot of you because they're all basically the same. And you know, I know these cycles are weird for you to look at because we don't do these in organic chemistry, but The parts that I think you'll all see again, just to point out the commonality, is step one, which I know, Emily, you and I talked about this briefly because yours is sort of the same, that you're beginning with palladium 0 and an RX compound, which would be an aromatic halide in Naya's case and many of your cases too. And then the palladium gets inserted in between the carbon halogen bond, and it becomes oxidized from palladium 0, which means just the metal, to palladium 2. So it's oxidative with respect to the palladium, and it gets inserted. So sometimes people call this oxidative insertion or oxidative addition. And it's similar, if you think about it, to making a Grignard reagent. If you remember a Grignard reagent, you have an alkyl halide or an aryl halide and magnesium metal, and the magnesium gets inserted in between the carbon halogen bond. That's also an oxidative insertion. It's just that this then sort of continues. And then at the very end, the Heck reaction is the hardest one to look at, but at the very end, you have both the carbon groups attached to the palladium, which the Heck reaction is kind of not a good one to look at for this. That's actually in like part 3. And then by the end, the palladium does a reductive elimination. So it turns back in palladium 0. So it can like go through the cycle like again. And there's all kinds of like little details in there too, but those are like the key things. So that's good. Great. Heck reaction. That's about as much singing as I ever do. All right. Thank you, Naya. Can you put, Naya, would you mind putting your Heck reaction sheet in your, and everybody put your reaction sheets in your Sakai folder?
Yeah.
Yeah, thanks. All right.
I'll go.
Hey, Emily. Thank you.
Right. So this is what I collabed for the Suzuki reaction. So it's the functional groups that make it up are some boronic acid with an R group on it, and an organohalide, which is also called a halocarbon, and it's catalyzed by a palladium complex, like the Heck reaction. So this is just like a simplified Suzuki reaction, and oftentimes the R group are aromatic rings. This is just an example synthesis used in like real life of how the Suzuki reaction is used. So it's often.
Can I interrupt you real quick before you get started? Sorry, I'm sorry. I hate doing this, but
no, that's fine.
So I see in the synthesis box, sort of down on the left side. Do you see what I'm saying? So underneath the first box, the synthesis box to the left. Yeah. So actually this happened with Naya too. There's a word that I can tell that none of you are familiar with, and which is olefin. So I can tell you're unfamiliar with it because you spelled it wrong. So see polyolefins, it's not PH like dolphins, it's F like the other way F is pronounced, you know what I mean? So it's olefins like that. And olefins is not, oh, you are correct. You have like in parentheses alkenes. Olefins and alkenes are exactly the same thing. Olefins is just the old word that people used to call alkenes. They used to call them olefins. I don't know why. And people do it less now, but there's still some carryover. So
thank you for that.
Okay,
for correcting me on that, because I didn't know.
Yes.
Yes. Okay, so they can synthesize polyolefins or alkenes, styrenes, which are just like this benzene with an alkene on the adjacent carbon, and biphenyls, which is what the mechanism I'm going to show is, and that's what this real life synthesis shows, is a biphenyl. So the catalyst is a palladium complex. It kind of looks like this, just this general setup. So your ring, now that you bring up, this makes sense now. It's not an argon. I was confused typing it, but now that makes more sense.
Yeah, that's
Aromatic
unfortunate.
ring,
Yeah.
and oxygen with an R group. And I'm guessing these are 2 ligands.
Yeah.
And then
Like Naya said, oftentimes those are phosphines. Not always, but oftentimes.
okay. So the base here has 3 roles that could be used for. So it forms the palladium complex, forms the trialkyl borate, which is in like this step, which we'll talk about later, and it just helps the reduction elimination step go by faster, like through the reaction that's like a byproduct of it. So I put this on a bigger page so it's just easier to see. So this is good, like the first step. It starts out the same as Naya's. So it starts with this ground state palladium and its oxidative addition. I kind of made that way too small, but it says the palladium inserts itself between the ring and the halide. So the addition here and the oxidative part are referring to the metal, and same with the reduction and elimination. They refer to like the palladium, not so much what's attached to it. So when this becomes a charged palladium, when it's like inserted between this bond.
That's the part that's just like a Grignard, right? If that was magnesium, you would have just made a Grignard. Yeah.
Mm-hmm. And so this is where it's like the whole thing is similar to Naya's step, but it's kind of in a different order because here the base is used to, remove the halide and then put the oxygen T-butyl group on the complex. And here we have transmetallation, which you could see here. This is like the boronic acid, and it's this is where the base is used to make the borate, the alkyl borate. So now a new base was used, which is why I represented it with purple, to put an oxygen T-butyl group on a new R group, which is why it's orange. And like this is a little side product that's made in order to make this complex where the palladium is between the 2 phenols. And now in the last step, the reductive elimination, the palladium is gone and the phenols are attached to each other. So the palladium is reduced and it's eliminated from the step, and you go back to having it at 0. So we know it's a catalyst because it was like regenerated at the end and not used up. And yeah, that's everything, I think.
Yeah, the Suzuki I think is the oldest of all of these reactions, and like I think everybody thinks about all these reactions in terms of how they're similar or different than the Suzuki reaction. But again, it involves an initial oxidative insertion of the palladium, and then by the end you have both of the coupling partners, both of the carbon groups on the palladium, and then the palladium becomes reductively eliminated, and then the carbon groups bond to each other. So that's also like a very common theme for most of these reactions. Yeah. All right. Very nice use of color too.
I can go next.
Okay, Beth.
So mine is a bit different because it's an amination. It's the formation of carbon-nitrogen bonds instead of carbon-carbon bonds. So this is the Buchwald-Hartwig amination. And obviously the 2 scientists involved were Stephen Buchwald and John Hartwig, and they published a variety of papers on it between 1994 and 2000. So it wasn't just one discovery, it was like successive. They kept making it better. So the starting materials are aryl halides or pseudohalides, which I learned are inorganic compounds that are equal in electronegativity, charge, and reactivity of halides. So an example I put here is a cyanide, but can also be isothiocyanates, sulfhydryl groups, azides, and triflates. And the other coupling partner are primary or secondary amines. So the catalyst and the conditions, once again, it's a palladium catalyst, which can be bound to a variety of ligands that I have shown down below. Its basic conditions, much like the other reactions. The solvent is usually toluene or DMF. Most of the ones I found used those 2, so I assumed to generalize it, and they're normally heated to approximately 100 degrees Celsius. And here's a simplified reaction scheme. So there's the aryl halide, which X could be either chlorine, bromine, iodine, or this is a triflate, I think. That's how it's.
Yeah. And triflate is, we've seen a lot of like variations on tosylate. Remember, like the mesylate group has come up quite a bit. Triflate is trifluoromesylate, right? So remember, mesylate, it's just a methyl group on the sulfonamide. So a triflate is a trifluorinated one. So that thing is that's probably the best leaving group in like known, right? So it's like a supercharged nitro in the gas tank version of tosylate or mesylate. Okay.
Cool. And then there's your primary or secondary amine, the catalyst, which is palladium bound to a ligand. The reason it's generalized is that there's so many that are used. And then the base, for example, is potassium terbutoxide, and you end up making an aryl amine. So here's the catalytic cycle. Like Scott mentioned, it's basically the same for all of them. So oxidative addition, so the palladium is oxidized. It kind of just sticks itself between the aryl group and the halide, or that leaving group. Then that nitrogen group that you're trying to add, the primary secondary amine, coordinates in and forms a bond between the palladium and ejects that halogen, that leaving group. Then here's the potassium terbutoxide, which kind of exchanges and takes the halogen with it, basically. And then there's the reductive elimination, where the electrons go back to the palladium. The aryl group forms a bond with the amine, and through reductive elimination, you have your aryl amine, and the palladium goes back to being palladium 0. And originally, I kind of struggled finding the applications of this, but then I stumbled on a literally 86-page paper titled Applications of Palladium Catalyzed Carbon-Nitrogen Cross-Coupling Reactions, published by Stephen Buchwald in 2016.
Yeah.
And so this is one of the schemes he used, and it shows how useful this particular reaction is because of the importance of carbon-nitrogen bonds, especially in biologically active small molecules. So here's medicinal chemistry. Process chemistry is optimizing the procedures to make compounds for drug development. Material science, synthesis of the ligands themselves, which is interesting. So you can use this reaction to actually make ligands for further reactions. Natural products and heterocycles, which is like an extra step. And so the example synthesis I found down here is a serotonin and dopamine reuptake inhibitor, SDRI, which is also known as an antidepressant. So this is how they did that using this cross-coupling reaction. So there's the iodine that ends up leaving, there's the nitrogen coupling partner, and they end up attached to each other.
Oh, that's an interesting example, because you can see that it preferentially aminated the iodine position in preference to the chlorine position. And actually, at least for one of you, that was true for the epibadidine synthesis, because I think some people had that aromatic ring with an iodine and a chlorine, and it was the iodine position that got added to the larger scaffold, just showing that as you go down that halogen what's vertical column, as you go down that column, the leaving group ability increases as you go down, so you can get away with that, it's good.
And then the double arrows just indicate like removing that Bach protecting group. And so what I wanted to show on the second page is also from that same super long paper, is the variety of ligands you can use. And like, this isn't even all of them. So there are so many, and they're not all that similar. I learned what AD means, which is adamantane, and it looks like a diamond. It's like 3 rings on top of each other. But this one's probably the simplest, triphenylphosphine. And then there was one mentioned up at the top, which was palladium acetate. And then there's a bunch of others. The ones I thought were interesting were the ones that had like people names down here. I don't know how that came around, but that just goes to show the variety of ligands you can use, and the fact that this reaction can be used to make ligands such as one with carbon heteroatom bonds. So that's this one.
Great. Thank you, Beth.
Okay, how do I turn this off? There it is.
There you go.
Okay.
All right, Lindsay.
Yes.
You had the Stilly reaction?
I
You
do.
did.
I do. Can you guys see that okay? Is it like big enough and stuff?
If you can make it a little bit bigger, I think that would help.
Okay, we can.
Oh,
we can
wait. Can you maximize the window of the presentation?
I actually, my notes are on the other screen.
Oh, okay. That's good. Right there, right like that, I think is good. Yeah.
So they're not printable notes.
Lindsay, this is so pretty.
Thanks. Okay, so I'm talking about the still reaction, which is basically the Heck reaction, except if you remember in the Heck reaction, on the R2 substituent, there was a hydrogen, and so basically they just replace that hydrogen with a halide group, and the reaction forms two carbon-carbon bonds between R1 and R2. And this SNR3 is a, actually I'll talk about that in the functional groups, but it retains stereochemistry as well. So you can see R1, which is bound to the SNR3, is either an alkyl, alkenyl, aryl, or vinyl. R2 is acyl, alkenyl, allyl, aryl, benzyl, or vinyl. And then X is halides, except they said that chlorides don't really work that well, so they generally don't use those. And then a couple of these others, like OAC, we talked about, we used a lot in Orgo 2. And I actually don't know what this is.
Yeah, that's sort of like a that's a phosphate group or a phosphoester group. Yeah, just another sort of leaving group. Yeah.
Yeah, I figured.
What's remarkable about this, if you notice the list of R groups, is that the Stilly reaction, you are not restricted to making bonds between sp2 hybridized carbons, which was true for the Suzuki and the Heck reaction, right? Yeah. Where you're making bonds between aromatic rings or an aromatic ring and an alkene. Here you can couple many more different kinds of carbons, which it makes it more, it has a broader scope.
Right.
Yep.
And then, so SNR3 is an organostannane, I think is how you say it, which is basically just tin with hydrocarbon substituents. And then the reaction conditions is it's palladium catalyzed. It's generally PD0. And then they usually have two ligands, and something about this reaction is so wide used because it pretty much works in any condition. Like, it just doesn't need anything really besides the palladium catalyzed. So, and then my synthesis for this was the synthesis of uracil A. And you can see right here, this is where they add the SN-Bu3 to here, and you can see the bond form, like the Br pops off, and the bond forms between this carbon and this carbon right here. And you can see it form right there. And then they also have a Diels-Alder and then 12 other steps that leads to uracil A, and it's an anti-tumor drug. So, yeah, I thought it was pretty cool.
Yeah.
And then this is the catalytic cycle. It's pretty much the same as everybody else's. It starts with palladium with an oxidative addition in which RX is added and palladium kind of like inserts itself in the middle of it, like we talked about. It's also a concerted reaction. And then there's transmetallation, which the tin and the R group form a 4-membered ring. And palladium at that point is in an 18-electron transition state. And then tin halide leaves, and then the R group stays bound to the SN. Yeah. And then, so usually this forms either a cis or trans orientation, and it has to be in cis for it to continue on to reductive elimination. And so then it goes through some isomerization to make sure that they're all in the cis position. And then reductive elimination just regenerates the catalyst and completes the coupling. So
Great.
yeah.
Nice, Lindsay. That's the world of palladium.
It's a very large world.
It's yeah, and we have not, and I just pick sort of like some of the ones that are the most used. There are many, many others. There's the Sonagashira reaction, the Negishi reaction. There's a bunch of these palladium catalyzed cross coupling reactions. But they all kind of work the same way.